Grab a pair of frames from a video and lay them side by side. To your eye, the difference is obvious. The car slid left, the runner leaned in, the camera drifted up. But a machine sees only two flat grids of pixels, with no built-in notion of movement at all. Optical flow is how we hand it that notion. It measures, for every pixel, exactly how far and in which direction that pixel moved from one frame to the next. That measurement turns raw video into something a computer can actually reason about, and here's how that works. Now, to feel why this matters, compare a single frame with a flow field. A single still frame carries no sense of motion whatsoever. You can see what's in it, the objects, the colors, the layout, but nothing tells you which way anything is heading or how fast it's going. Freeze a video on one frame and every trace of the movement simply vanishes. Optical flow restores that missing dimension. It produces a dense field of vectors, one little arrow for ideally every pixel, showing how far and in which direction that point traveled between the frames. Suddenly the machine can see the motion as clearly as you do, with direction and speed baked into every single pixel of the image. To understand where those vectors come from, let's trace the estimation through the classic pipeline. It starts with a pair of consecutive frames from the video. That pair is the whole input, nothing more. The question the method has to answer is simply where each point in the first frame ended up in the second one. The core assumption comes next. A point on a moving object is expected to keep roughly the same pixel brightness as it shifts. So if a bright speck moves, you can look for that same brightness nearby in the next frame and reason that the speck went there. Then the matching happens. Because a single pixel's motion is genuinely ambiguous on its own, an issue known as the aperture problem, methods add a smoothness assumption, the idea that neighboring pixels tend to move together, and then solve for one consistent set of matches across the whole frame at once. And the output is that dense field of motion vectors. Classic algorithms like Lucas and Conade, which track a sparse set of points, or Horn and Schunk, which solve for dense flow, compute this directly, while modern networks such as FlowNet and Raft learn to estimate it far more robustly from data. Alright, let's pull out the ideas that hold this whole topic together. Dense motion, pixel by pixel. At heart, optical flow gives you a motion vector for every pixel between two frames. That density is exactly what separates it from just tracking a handful of feature points around the scene. The founding assumption. Classic flow rests on brightness constancy, the idea that a point keeps its intensity as it moves, plus a smoothness prior so that neighboring pixels tend to flow together and the ambiguity of a lone pixel finally resolves. Where it pays off. Flow powers object and camera tracking, video stabilization, and compression that cleverly encodes motion instead of whole frames, along with action recognition, slow-motion frame interpolation, and visual odometry in robotics. Occlusions, large or fast motion, and flat textureless regions remain the genuinely hard cases that trip these methods up. Okay, let's lock in the 4 takeaways. Optical flow gives you a motion vector for every pixel between 2 consecutive video frames. A dense field of tiny arrows describing exactly how the scene moved. Classic methods build on brightness constancy plus a smoothness assumption, which together resolve the ambiguity of a single pixel's motion. Modern deep networks like FlowNet and Raft learn to estimate flow far more robustly than the older hand-designed algorithms ever could, especially through occlusions and fast motion. From tracking and video stabilization to compression, action recognition, and slow-motion frame interpolation, flow quietly drives a lot of video tech. Want more of these explainers in plain language? Standarity.com is where they live.